Yeah. So today we'll discuss about this what we call. So last class is it fine? Just we discussed about the data types and what are the data types and all those things. Is it fine? Hope my screen is visible. Just give response, so that I.
Yeah, it's
Oh yeah,
visible. Yeah.
yeah. So today we'll see the port rule connections. Port rule connections. So port rule connections, suppose like if you take a full adder circuit, okay, if you take one full adder circuit, this is a full adder circuit. So you have three inputs. Let us take A, B, and C in, and outputs are sum and carry. Okay, outputs are sum and carry. So, so how you are writing this full adder means basically suppose if you want to write the test bench for the full adder, first you need to write the design for the full adder. Okay, so first you need to write the design for the full adder. So this is the design for the full adder. So this is full adder, and the inputs. So whatever the inputs, so you are writing. So input for this design has three inputs and two outputs. And if you are writing the test bench, this is nothing but the top module. Okay, so you are writing the test bench for this full adder. So so if you see so for the test bench also you are giving some inputs. So these are the inputs A, B, and C in, and sum and carry. And for the test bench you are giving A underscore TB and B underscore TB and C in underscore TB, and outputs are S underscore TB and C underscore TB. Okay. So here, so if you see for the design, so for this design, it should be for this design it should be netted data type. It should be netted data type. Okay, and for the test bench inputs, it can be reg data type or it can be net data type. It can be reg data type or can be net data type. And coming to the outputs of this design, this is my design. Okay, so for the output for the design, it can be net or reg data type. And output for the test bench, so this should be net data type. Okay, so these are the port rule connections. Okay, so these are the port rule connections. So normally when you are doing a top level module, so these rules we need to follow. So that means here, so in general you can consider this is my design. Okay, this is my design. So input for the design, so these are the input for the design. It should be which data type means the ports we need to declare with net data type. And coming from the instances. Okay, so coming from the instances, this is it can be net or reg data type, and there are some inout ports also. So for inout ports, for the design, there are some inout ports. It should be net data type for the top module, and it also for the design, it should be net data type. And coming out for the from the design, this is reg or net data type, and output should be this should be net data type. Output should be net data type. Okay, so so these portal connections you need to consider. Okay, so so if you consider like one example, I'm writing one second. Yeah, suppose if you write the code for the design. Okay, so code for the design, suppose if you are writing for and gate. Okay, so and gate, so test bench I will tell you afterward, but But for the AND gate or any off adder circuit, full adder circuit, first you need to design, and whether your design is working properly or not, then you need to, for the verification purpose, you need to write the test bench. Okay. So simple AND gate I am writing. So this is a simple AND gate. So for the AND gate, you have two inputs A and B, and output is what, A and B. Okay, this is output is A and B. Okay, so for this, first you need to write the design. Okay, this is my design. Okay, this is my AND gate. This is my AND gate. Okay, so inputs are, what are the input for this AND gate? A and B, and output is what? Output is Y. Okay, so, and coming from the top module, you are writing for the verification. For this design, you are writing the test bench. For this design, you are writing the test bench. So for the test bench also, you have some input for the test bench. Let us take A underscore TB and B underscore TB, and output is what? Y underscore TB. Okay, so that means for the input for the design, you need to consider like these are net data type. They should be net data type, and input for this test bench can be reg data type or net data type, and output for the design is net data type or reg data type, and output for this test bench should be net data type, should be net data type. Okay, so like so that means how you are writing the code means you can write this code by using gate level modeling or data flow modeling or behavioral modeling. So if you write in behavioral modeling, I will tell you separately what is behavioral modeling. Module, and what is my module name? And underscore gate, and underscore gate, this is module name or identifier, and I need to declare, so input A comma B. So by default, you are not declaring any data type. By default, this is Y data type. This is nothing but Y data type. Okay. So net data type, in that net it is Y data type, and output when you are using behavioral modeling, output should be reg data type. Okay, and I am writing always at the rate star. So in bracket, this is nothing but sensitivity list. If there any change in the inputs, then there is a change in the outputs. So that means if you have 100 inputs and 100 inputs or 200 inputs, so it's difficult to write in the bracket. If it is star, so this is we call as implication operator, implication. So that means we are writing star means that will be applicable for all the inputs. Okay, so I am writing begin y equal to a and b, y equal to a and b, and end module. Like this, I can write a simple and gate program by using this behavioral modeling. This is nothing but behavioral modeling. I told you, no, behavioral modeling you need to write within the procedural blocks. That to always block we need to write. Initially, it's not synthesizable, so that's why we need to write by this one. Okay, so suppose I want to instantiate, suppose two or more gates are there. Okay, I need to do like a instantiation. Okay, I can call two times, four times, or five times. Okay, that is nothing but instantiation. Okay, so in the instantiation there are two types are there. Instantiation. So instantiation, there are two types are there. One is connection by name, connection by name, and next one is connection by position, connection by position with order list, connection by position with order list. Okay, first we will see the connection by name. What is this connection name? Connection by name we will see. Okay, so connection by name, so connection by name is here. So you need to declare like input should be so I'm writing for the test bench. In the test bench, how you need to write means I'm writing that is module test bench for the AND gate module TB. Okay, so I'm declare uh, inputs can be wide data type. The connection by name, the syntax will be like this. Syntax will be, so how the syntax will be there? So it will be like this. Uh, design name, design name followed by instance name. Design name followed by instance name. Okay. So design name followed by instance name. So like how it will be there means design name. So what is the design name? So dot a, and in bracket what you will get a underscore tb. This is the test bench inputs, comma dot b, okay, b underscore tb, comma dot y underscore tb. Like this you will get. Okay. So this is nothing but whatever the design port, design port, and this is the variable of test bench, variable of test bench. Okay. So first you declare the test bench variables are a underscore tb, b underscore tb, and c underscore tb. Okay. And next and so inputs normally you can declare with reg or wire. Here you can declare with reg also. Okay. And output should be wire data type. So output should be what? Wire. Okay. Wire net data type means wire y underscore tb. This is output. Okay. And how I am writing, that means design name. What is my design name? So whatever I wrote in the design, that should match in the test bench. Okay. So my design name or identifier name is and underscore gate. No. So this name and whatever you are instantiating, that should match. Okay. And underscore gate. So and instance name. What is the instance name? Let us take A1. Or you can, instance name is optional only. You can write a DUT or a UUT, unit under test. Okay, anything you can write. Okay. Dot a underscore tb, comma dot b underscore tb, comma y underscore tb, y underscore tb. Okay, like this you need to write. Okay, this is nothing but what? Connection by name. Is it fine? Do you understood how I am writing the connection by name?
Yes.
Okay, yeah. So next is connection by position with order list. So connection by position, with order list. So connection by position with order list means how I am writing means here. So normally you write so for the AND gate you write the I'm writing the code by using data flow modeling. So A B and Y equal to what? A and B. Okay, Y equal to A and B. So module, okay, and underscore gate. Okay, this is the design I'm writing. So you need to declare the inputs. Okay, input A comma B. So by default, you not declared any data type means this is a byte data type, and output y. Okay, output y. I am using a continuous assignment statement, that is assign y equal to what? A and b. Y equal to a and b, and a and b, and end module. Okay, so this is my design. And if you want to write for the test bench, okay, in the top module, okay, and write, I can write module top. Okay, module top. So let us take so input should be reg or y data type. Here I am writing reg x comma y comma z. Okay, these are the variables for the test bench. And instance name and underscore gate, and underscore gate. This is optional only. Whatever you want, you can keep. DUT, UUT, IN instance one. Okay. Design variables will come outside the bracket. Okay. And text bench variables will come inside the bracket. Okay. So dot A X, dot B Y, and dot Y Z. Okay. So this is nothing but what? Connection by name. Okay. End module. Okay, this is nothing but my connection by name. Okay, connection by position means So how I am writing, this is nothing but it is a connection by name. Connection by name. Okay. So connection by position with order list means design will be same only. Okay. This is whatever the design, this design will be same only. So connection by position with order list, how I can write means connection by position, connection by position. Here, so how I can write means, so how you declared these inputs and outputs, that order you need to follow. Okay. So first A and B will come and Y will come. Okay. Similarly, here connection by position with order list, how I am writing. So module top, module top. Okay. So I can declare wire or edge. Okay. So it can be a wire or edge data type. I am using edge data type xyz. Okay. So I am instantiating this design. Okay. How I am instantiating it? And underscore gate, this is nothing but my instance name. Okay. This is my design name followed by instance name. Okay. inst1. Okay. You can keep dut or uut. So how you declared these inputs and outputs in the design, the same position or same order list I need to follow. Okay. So in place of a, x is there, and in place of b, y is there. In place of y, you have z is there. Okay. Z is there, and end module. End module. This is nothing but connection by position with order list. With order list. So did you understood how to means how to instantiate the design with order list?
Yeah. One doubt actually, if
Yes.
you're declaring that variables inside the module, then we can't use this connection by position.
Inside the module means where you are asking?
I mean, we are just starting module and gate and inside that, right?
Yes.
Here we are declaring that variables in the same line, right? Input A, B.
Normally, like for the verification purpose, we need to write the test bench. Okay. So
Mm-hmm.
for the test bench, what you need to do means you need to declare the internal variables, and after that you need to instantiate this design. So that instantiation can be two types. One is instantiation by name and instantiation by position. When I tell you the test bench, it will be more clear. But I will tell you one more thing. Like in digital, you designed full adder by using half adder, no?
Yeah.
Full adder by using half adder means first I can write the program for half adder, and I can instantiate how many times? Two times. Okay, this is
Yes.
nothing but one type of we call as structural modeling. This is structural modeling. Okay, so I can instantiate by connection by name or connection by position. Is it fine?
Okay.
Okay. Yeah.
Yeah, I got it. Yeah.
Yeah. So similarly, parallel adder also. Parallel adder. So parallel adder means what? We are designing the parallel adder. That means ripple carry adder or BCD adder or carry look adder. We are implementing those parallel adders by using full adder circuits. Okay. So there we are using four full adder circuits. Okay. So that means every time we can't write the code for each full adder. The programming length will becomes complex. Okay. So one time I will write the program for full adder and I will instantiate four times. So that program complexity will decrease. No? Program, the number of lines I am writing the program will decrease. So that
Yeah,
is
yeah, understood.
this advantage of this is instantiation. Okay. So this is nothing but structural model. Structural model. Okay. Structural model. So that I will tell you. So in digital you already studied like full adder using half adder, full adder using half adder. Okay, how many half adders are used in the designing? Full adder using half adder,
Two.
two half adders and one OR gate, no, one OR gate.
Yeah.
Okay, so here how I am designing means I am taking one half adder. This is one half adder. Okay, let us take this is half adder one, and this is one more half adder two. half adder 2. These inputs, let us take the inputs are A and B, and outputs are sum and carry. Outputs are sum and carry. So this is given to one more half adder. One more half adder. This is one more half adder A and B, and this is sum and carry. Mm. So uh, this is the output, means we are getting the output, two outputs. Okay. So let us take the internal variables. So internal variables are you need to declare the internal variables. Let us take W1, and here C, this is not W3. So I am writing this one under the top module. This is under the top module. So this input is nothing but A underscore FA, and B underscore FA, and and this one is given, C is given as one more input, and this is given to an OR gate. This is given to one OR gate. This is given to one OR gate circuit. One OR gate circuit. Here you are getting a carry as output. And this is sum. And these outputs are sum underscore FA, and carry underscore FA. Carry underscore FA. Okay. So internal variables, here also I need to declare the internal variables. This is W2. This is net data type. Internal variables are nothing but you need to declare with net data type. Okay. So this is also W3. You need to declare with net data type. Okay. So first, what you need to do, you need to write the code for half adder circuit. Okay. First, you need to write the code for half adder circuit. So like I'm using the data flow modeling. So module half underscore adder input A comma B, and output sum comma carry. Okay. Output I can write here S comma C is there, no? So I can write this is S comma C. One second. Output is S comma C. Output is S comma C. S comma C. Okay. Output S comma C. And I'm using the data flow modeling. That is, I need to use a continuous assignment statement. Assign that S equal to what? A XOR B. Okay. This is nothing but bitwise XOR gate. This operators will discuss separately. Bitwise XOR gate. Assign carry. So that is C equal to what? A and B. We know that for the half adder circuit, sum equal to what? A XOR B. Okay. And carry equal to what? AB, that we seen in the digital. Okay. So, and end module. Okay. So this is my design for the half adder circuit. Okay. After that, I need to write the code for full adder circuit. How I can write? So module name is full adder. Input, what are the input? A underscore FA, and B underscore FA, and one more input is there. One more input is this one. Cin underscore FA. It is coming, and it is, we are giving as input to this B. Okay. So Cin underscore FA, comma output. Okay, here I can write output sum underscore FA, and carry underscore FA, and I need to declare the wires. How many internal wires are there? So that is wire W1, W2, and W3. These are the wide data type. So the first half underscore adder, okay, adder. Let us take this is HA1, no? HA1, this is an instance name. I'm doing like I'm using connection by name dot A, okay. This is the design variables A underscore FA, comma dot B underscore FA, comma dot S, okay, dot S, and what is the output for this W1, no? So W1, okay, comma dot C, and what is the output W2, okay, and half underscore adder HA2 dot A for this W1 is the input, okay. So W1, the top module W1, so this is the design input, so W1 output the top module, and B, okay. So for the B, Cin underscore FA, Cin underscore FA dot S, sum underscore FA, sum underscore FA, comma dot C, uh, W3, dot C W3, okay. And next last I need to assign, I'm using a continuous assignment statement, that is assign uh, carry underscore FA, okay, carry underscore FA, that is equal to W1 W3, W1 W3, W1 W3, and end module, okay, end module, end module. So like this, you need to instantiate. First, you need to write the code for half adder, and then next you need to instantiate by two times. So that is a connection by name. Connection by position means you need to follow that. So you need to follow the how you declare the inputs and output. That same thing you need to follow in the connection by position. Is it fine?
Yes.
Okay. Yeah. So so here I'll show you one code related to this. One second. Mm, mm, Verilog program. This one, full adder using half adder circuit. Full adder using half adder circuit. It will open. One second, I will open the project. Yeah, see here. First, I wrote, so this is full adder using half adder circuit. So here, like, first I wrote for the half adder circuit. Okay. So this is, hope this is visible. It's fine.
Yes.
Okay. So this is full adder using half adder circuit. First I wrote module half underscore adder input A comma B output sum comma carry and assign sum equal to A XOR B assign carry equal to A and B and end module. Okay. So this is the program and here I am writing full adder circuit. This is the if I write one second full adder circuit instantiation I need to half adder 1 and half adder 2. Yeah. So here this is full adder circuit. So full adder circuit, same thing I explained, no? So this one first full adder. So module full adder input A underscore FA, B underscore FA, output sum underscore FA, carry underscore FA. Okay. So the internal variables those are wire W1, W2, W3. I need to declare and this is I need to instantiate two times half underscore adder HA1 dot A. Okay, dot A underscore FA dot B underscore FA sum W1 dot carry W2 and half underscore added HA2 dot A W1 and B C underscore FA dot sum underscore FA dot carry underscore W3 and I need to use the continuous assignment statement assign carry underscore FA equal to W3 or W3 okay W2 or W3 okay. So this what I need to do I need to like I need to elaborate the design okay. I want to see the design how the design will look like. Just one second. Full ladder. This should be top model. So if you see, if you elaborate the design, it will show the design how the. So that means you are writing the program in the Verilog. So the tool will convert into the netlist. Okay, design. Okay. For this, you need to elaborate the design. One second. It's elaborating the design. Yeah, I will close this. Whatever the design you want to do. So this is two modules are there. So this is different module. So I am drawing the half adder by using full adder. No, you need to go to right click and you need to make a top module, set as top. Okay, so that will make as a top module and open elaborated design. Okay, now it will make the design. So we are designing the half adder by using two full adder by using two half adders. So I want to see the design. See here. So have you observed? That means I designed the full adder by using two half adder and one OR gate. Okay.
Yeah.
So the inputs are A and B and outputs are the for the design are carry and sum and here also. And if you expand this, okay, one more input is coming. That is if you expand. So this is one half adder circuit. Okay. So the tool is converting whatever your code into the hardware.
Okay.
Okay. Yeah. So like this, you can see your design. Okay. Yeah. So this is about the instantiation. So next, one second. So next we'll start. So like this, you can design the full subtractor by using half subtractor also. Okay. first you need to write the Verilog code for half subtractor, and next you need to, so you already designed the full subtractor by using half subtractor, so you need to write instantiate this half subtractor by two times. Okay. Similarly, you can write the code for ripple carry adder also. Okay. So just ripple carry adder, I will show you just 1 second. Ripple carry adder. Verilog codes. This also I will share, don't worry. Mm, mm, this is 4-bit subtractor. Yeah. So this is 4-bit subtractor. So it can be add as a, it can be used as adder subtractor also. Okay. So adder subtractor. So here, if you see this code, just you need to. This is GBIM. So GBIM is open source. So this is a powerful editor. So when you are using the model sim or Quasta sim, you need to use this GBIM software. So first I wrote the full adder program, module full adder, input A comma B comma C in, output sum comma C out. Assign sum equal to what A X or B X or C, assign C out equal to AB plus BC plus C in, and end module. This is nothing but my basic top level data flow modeling. I'm writing in terms of data flow modeling, and I'm using, that means I'm designing the module ripple underscore carry underscore subtractor. So like input 3 down to 0 A comma B, and there is a control is there. Okay, there is a M pin is there. When you seen in the digital M pin, when M equal to 0, that is like, that is acting as a M equal to 0, that is acting as a parallel adder. When M equal to 1, that is acting as a parallel subtractor. Okay, so here I am using a control, like a input control, and output is nothing but I'm using a vector 3 down to 0. How many inputs? That is S comma C out, and I'm initializing one more internal output. Okay, that is BC. BC as 3 down to 0. So that means A is directly given, but that B is given through this control pin. Okay. So when control pin equal to 0, that is A XOR 0 equal to A itself. Okay. It is acting as a parallel adder. A XOR 1 equal to A bar. No. So that means this is given through the control pin, and normally it is doing the 2's complement subtraction. So you are getting BC of 0 equal to B of 0 underscore XOR of control, and B of 1 equal to same thing, B of 2, B of 3. Okay. Next you need to instantiate. How many full adders? That is 4 full adders. So full underscore adder. So this is a design, and instance name FA of 0, A0, BC of 0, control, S of 0, C out of 0. Okay. So when control equal to 1 means it will do the 2's complement subtraction. Okay. So when control equal to 0 means normal parallel addition. Like it will be act as triple carry adder only. Okay. So I have instantiated 4 full adder. That is full adder 1, A of 1, BC of 1, C of 1 acting as an input carry for the first full adder. Okay. S of 1 and C out of 1. Similarly, A of 2, BC of 2, C out of 1, S of 2, C out of 2, and A of 3, BC of 3, C out of 2, S of 3, C out of 3. So this is how you can write the code for adder subtractor cycle. Do you understand?
Yes.
Okay. Yeah. So this I will share. Don't worry. Yeah. Uh, so next is introduction to the gate level modeling. Okay, so we already discussed that 4 styles are there: one switch level modeling, gate level modeling, data flow modeling, and behavioral modeling. Okay, so like gate level modeling. So gate level modeling means uh, so you have some gate level primitives are there. Okay, so what are the gate level primitives means you are using so these and or not, okay, and NAND, NOR, okay, and next we have XOR, XNOR, XNOR. Okay. So like this, you have so gate level primitives. Okay. So gate level primitive. These are built-in functions. Okay, already there. These are built-in function. Built-in function. Okay. And next buff if 0. Okay. Buff if 0. Buff if 1. Not if 0. Not if 1. These are some gate level primitives. Okay. Suppose for the AND gate. Okay. So the syntax will be so how the syntax will look like means mm, so like you have a gate level primitive. Okay. So gate level primitive, and this is gate level primitive. Okay. And gate level instance, gate level instance. This is optional only, followed by output and input 1, input 2, up to so on, input n, like this. Okay, this is the basic syntax for gate level modeling. Okay, so here, like suppose if you take, so suppose if you suppose this logic gate is there, suppose half adder is there. Suppose if you consider half adder circuit, this is A, B, and output is AB, AB. So here this is sum, and this is carry. Okay, sum equal to what? A XOR B, no? A XOR B. Carry equal to A and B. Okay, A and B, AB. Carry equal to A and B. Okay, so how you write in a gate level modeling? That is, so you are writing sum. So that means so gate level primitive. So that means XOR. Let us take the primitive name is A1, and this is A2. Okay, so A1 followed by output. What is output? Sum, comma A, comma B. Okay, like this you can write. And next carry. Carry means what? And gate level primitive is and. Okay, so gate level primitive is you are writing and gate level instance A2, and here you are using the output carry A, comma B. Output followed by the inputs. Okay, like this you need to write. Okay, suppose you have this diagram. Let us take one second. Yeah. So you have this diagram. This is given to one more uh, OR gate. Let us take OR gate. Okay. The inputs are A, B, and intermediate variable I need to consider as W1, and this is let us take C. Okay, and this is Y. Okay, so let us take the gate level instance name is A1 and A2. So how you are declaring? So this is AND, gate level primitive is AND, followed by gate level instance A1 and output W1, comma A, comma B, and or gate level primitive A2 and output, what is the output of Y, followed by W1, comma C. Okay, so like this you need to do. Okay, so like this. So similarly, so that means AND gate is there. So AND gate is there. So AND gate, how we are writing A, B and Y, and A1 is there. So how we are writing gate level primitive and gate level instance followed by Y, comma A, comma B. Okay. Similarly, OR gate. OR gate, how we are writing? This is the OR gate. This is the OR gate A, B and Y. Okay. So OR gate. Um, so for this you are giving R A, let us take A2 Y, comma A, comma B, like this. Okay, similarly XOR, so this is XOR gate A, B, Y. For the XOR gate you are using XOR XOR A3. Let us take this is A3. A3 Y comma A comma B. Similarly, XNOR also. So this is bubble A B, and this is the gate level instance is A4 Y, and you are using XNOR A4 Y comma A comma B. Okay, and next NAND gate AB and output Y. You are using a gate level primitive, that is a NAND, followed by gate level instance. Let us take gate level instance is A5. So output Y comma A comma B. Output followed by input. Okay. Similarly, NOR gate. This is NOR gate AB and output Y, and NOR followed by A6 Y comma A comma B. Okay. And next you have mm, uh, buff if 0 and buff if 1. Buff if 0, buff if 1 means, so suppose if you take buff if 0, buff if 0, okay. So buff if 0 means what? Buff if 0 means, so this is it is acting as a tri-state buffer, okay. So it is acting as a tri-state buffer. Uh, so uh, so like there is an enable pin A and output Y. Okay. So buff if 0. So buff if 0 means what? When enable equal to 0, Y equal to what? A. Okay. When enable equal to 1, Y will be in which state means high impedance state. Okay. So how to write like that? So how to write for this buff if 0? So for the buff if 0, you should write buff if 0, buff if 0. So instance name, let us take instance name a1 followed by output comma input. Okay, so you can consider enable as input only, input e comma a. Okay, so this is buff if 0. Okay, next buff if 1, buff if 1 buff if 1 means what? This is also tri-state buffer. So a b, and this is instance a2, and here enable buff if 1 means what? When enable equal to 0, it will be high impedance state. When enable equal to 1, it will be buffer, it will be act as buffer. Okay, output Y. So how I can write buff if 1, buff if 1 a2 Y comma E comma E. Okay, like this. Okay, similarly you have not if 0. Not if 0. Not if 0 means what? Not if 0 means this is a NOT gate. Okay, NOT gate, and it is controlling by one more controlling signal, that is enable. So that means when enable equal to 0, it is acting as the inverter Y equal to A bar. When enable equal to 1, it will be in high impedance state. Okay, so you can write not if 0, not if 0. Let us take the instance name is A3. So output followed by input. Okay. Similarly, you have not if 1, not if 1. Not if 1 means this is the NOT gate or inverter. So you have input A and output. One more enable pin is there. Enable equal to 0, it will be in high impedance state, and enable equal to 1, Y equal to, it will be act as inverter. Okay. So not if 1 A4, this is the instance name A4 Y comma E comma E. So like this, you need to write the gate level modeling for this one. Okay, is it fine?
Yes.
Suppose if it is 2 cross 1 mux is there. Okay, suppose 2 cross 1 mux means here two inputs are there. Let us take the inputs are A, B, and 2 is to 1. 2 is to 1 mux, and output Y, and there is a selection line. Yes. Okay. So in the distal you wrote the Shannon's equation. What is the Shannon's equation? So Shannon's equation is when S equal to 0, so A is connected to output. When S equal to 1, B is connected to the output. Okay. So that means you can write Y equal to what? S bar A plus S into B. Okay. So just you draw the logic diagram. So so this is S. So S bar. So S bar and A. S bar A connected with an AND gate, and next yes, okay, this yes and A, and yes, it is coming like this, yes, and next this is B, S and B, and these are connected with OR gate. Okay, these are connected with OR gate. Okay, so how to write this code in the gate level modeling means, so here first you write the gate level instances. This is A1, A2, A3, A4. Okay, and this is the output. Okay, this is the output. How to write the code? So first you need to write the module. Okay, so module. So module. So the identifier should not start with the number, no. So I can use this underscore also. Underscore it will take, compiler will take 2 underscore 1 mux, 2 underscore 1 mux. I need to initialize the inputs. Okay, so input A comma B comma S. Okay, output output Y. Okay, output Y. I need to declare. Okay, and next I am using gate level modeling. No, so first not of first not I am writing not of A1 A1. So let us take the Y's internal variables. Y is W1, and this is W2 and W3. Okay, so first you need to declare the wires. Okay, internal variables, that is internal nets I need to declare. Okay, so how to declare these nets? So I'm writing wire w1 w2 w3. Okay, and next not of a1 instance name, output w1 followed by input. Yes, yes. Okay, and next and of instance name is a2 followed by what is the output? W2 w1 comma a. Okay, w1 comma a. Okay, so this is nothing but what? So you are getting s bar a, s bar a. Okay, one product term you got, and of a3 a3, and what is the output? W3 and s comma b. Okay, so this is nothing but sb. This is nothing but sb. Okay, similarly next r of a4 a4, what is the output? Y y. Okay, y w2 w3 w2 w3. Okay, so this is nothing but my y equal to what? So this is my y equal to, so my y equal to s bar a plus s into b, s into b. Okay, so like this end module, like this you can write the code for 2 cross 1 mux by using gate level modeling. Okay, is it fine? Do you understood? Shall I move forward?
Yes.
Okay, so your task is so you need to install that Vivado tool, the Linux Vivado tool. I will share the process to install that Vivado tool. You need to write the code for half adder, half adder using gate level modeling. Okay, and we already done half adder by using NAR and NAND. No? So you need to draw the code for NOR and NAND. You need to realize the half adder by using NAND and NOR. and for that also you need to write the gate level modeling. Okay, and full adder also, full adder using gate level modeling, GLM. Okay, and by using NAND and NOR. This also we realized using in the digital, and similarly full subtractor using GLM. Okay, we GLM by using NAND and NOR. Okay, and uh, full subtractor, uh, next half subtractor. Okay, half subtractor using GLM. Okay, half subtractor using GLM. 2 cross 1 marks I already told, and next 4 cross 1 marks, 4 cross 1 marks using GLM, and next 4 cross 1 marks using 2 cross 1 marks using GLM, okay, and next 3 is to 8 decoder, and 8 is to 3, 3 is to 8 decoder, it will be somewhat complex, or will 2 is to 4 decoder used, 2 is to 4 decoder, okay, 2 is to 4, 2 is to 4 decoder using 2 is to 4 decoder, 2 is to 4 decoder, and 4 is to 2 decoder, 4 is to 2 encoder, 4 is to 2 encoder, sorry, 4 is to 2 encoder, yeah, 4 is to 2 encoder, and 4 is to 2 priority encoder, using GLM, gate level modeling. Okay, so by next week I want this.